I will try to keep my voice down in case you would like to have a nap after the lunch. Let's move on here. We're still talking about layer 2, virtual private network services. We talked about layer 1 and different ways of doing this at Ethernet at layer 2. And the basic way of doing a layer 2 Ethernet virtual private network service is simply to implement a bridge. A bridge that interconnects two Ethernet LANs across the provider's infrastructure, and encapsulate the frames that are going in according to the format. I'm going to skip through some of these slides now and not go into details. If you want to look at the details, you have the slides available. So that would be the basic Ethernet virtual private network service. We just provide a bridge that interconnects two Ethernets with each other. But that is a rather fundamental, rather basic service, and you can elaborate on that and put more functionalities into the provider networks, so make a richer interface between the CE and the PE, between the customer edge and the provider edge, so to allow the customer to use more advanced services. And one such service is a virtual private LAN service, VPLS. And now we're coming back to this, where we talked about this abstraction, where we see the virtual network as a switch, a virtual switch, a single switch, because this is very similar to the service that IETF has standardized as the VPLS service. It means that the service that we get, the thing that you would connect to as a customer, is an Ethernet switch, a distributed Ethernet switch. So the provider network appears to the user as a single switch. It does all the layer 2 switching function. It does learning and flooding and those kind of things that an Ethernet switch is supposed to do. But it is really implemented in the distributed fashion in the provider's network. And then there are some flavors of that. There is yet another IETF standard which says that, well, this is a useful service, but in most cases we will really only be using this to interconnect IP devices with each other. So there will be IP routers that we interconnect. So then maybe we can simplify this service and remove some of the functionality to create a simplified service, which is called IP-only private LAN services. But it's basically VPLS, but with some simplifications for a specific scenario. And these different standards, different ways of doing Ethernet virtual private network have been picked up by the Meth for Ethernet forum, the MEF, and they've defined a set of carrier services which are very similar to what we have seen. There's something which is called the Ethernet virtual private LAN, EVPLAN, which is a multi-point to multi-point Ethernet service, Ethernet virtual private line, EVPL, and some other flavors. So these are being picked up by the Ethernet forum, and the Ethernet forum, as you probably know, their mission is to try to push the Ethernet out into the metro area, so that it's being used by providers to build metropolitan area network and standardizing Ethernet for that, and they are then on top of that building virtualized services as well. All right. Now, one important function here is that we need to be able to do discovery, meaning that the provider cannot, for a reasonably large network, sit down and configure all the routers, all the switches, all the elements in the provider's network for the customers. I mean, if a customer would like to add one more site to his virtual private network, then the operator needs to update this information into the network somehow. The one way of doing this is, of course, manually. to configure all the routers, all the switches, and say, well, now there's another attachment point to this particular virtual private network over in that at that PE over there, and then reconfigure the internal routing and so on. But as you all understand, this doesn't scale. You don't want to do this kind of things manually. You would like to have protocol support for it. You want it to be done automatically somehow. So we like to have a discovery function, an auto-discovery function, so that all the provider edge equipments, the PEs, will discover themselves automatically what are the VPNs connected to at this particular site, what are the clients, what are the customers that have VPNs which are connected here, figure that out, and distribute that information to the rest of the PEs, so that they internally then can set up all the routing between themselves, so they know how to direct packets to the different parts of the different customer VPNs. So figure out the routing, setting up the tunnels between them, and of course we also like it to be dynamic. So if something changes, then the PEs should be updated automatically, and this distribution should be propagated between all the places and all the sites all the PEs in the provider network. Okay, so how do we do that? Well, one option would be to say that, yeah, well, this is a new kind of functionality. We don't really have it in our existing protocols, so let's invent a new protocol for doing this. But this is not the path that the IETF has taken. So what they've done instead was say that, well, we don't have exactly this kind of functionality, but we have similar functionalities already in BGP, the inter-domain routing protocol. So let's use this functionality and do some extensions to it, so we can use it also for discovery functionality for VPN purposes. So BGP already has something which is called multi-protocol extensions, which means that it understands different kinds of protocols, and it can carry information that are specific to different kinds of protocol. So let's use this to create a multi-protocol extension related to VPN and VPN discovery. So the discovery of the members that are parts of the VPN, it says VPL as members here, but it should really be VPN members because it's really generic to different kinds of VPNs. So that is part of the function that we like to use, and we like to use also functionality for setting up and taking down pseudo-wires or tunnels throughout the networks. So there was a design choice here. There was a trade-off. Should we design a new protocol for this, or should we try to add this functionality onto an existing protocol? And then it turned out the BGP had something which was very similar in terms of functionality, and perhaps we could just extend that and use it for this purpose as well. And then there's a protocol called Layer 2 Tunneling Protocol, which is, just to mention, one of the protocols that we're using for tunneling, and it has support for setting up dynamically tunnels and maintaining and tearing them down. But I'm not going to go into very much details about that. So instead, I'm going to skip on to Layer 3 VPNs. Okay, Layer 1, Layer 2, Layer 3. So Layer 3 VPN is, well, it's a virtual IPv4 network, or IPv6 for that matter. It's a virtual IP network, which means that it has its own private network, its own IP address space. It's not part of the internet. It's a different network which is built on the same technology as the internet. It's built on IP, but it's not an internet. It's a different network. So if we're setting up an Layer 3 VPN, it means that the relationship between the customer and the provider is really a routing relationship. So they're speaking routing protocols between each other, OSPF, BGP, BRIP, whatever it might be. So that is the interface that the customer sees from the provider point of view. They're setting up a routing relationship between each other. There's sort of two ways of doing this. One is called RFC 2547 BIS, where we're using Similar to what we saw just in the previous slides, we're using BGP for the auto discovery functions. We're using BGP for distribution of routes internally to the VPN, and we're setting up MPLS tunnels between PEs. So this is also sometimes called MPLS VPN because it uses MPLS as a tunneling technology. So that's one way of doing it. The other way is a little bit similar to what we saw earlier on in the first part of this, where we're instead setting up, where we're virtualizing the network elements, we're virtualizing the routers, so we're building a network out of virtual routers across the network. So we're slicing the routers and then setting up tunnels between them. I said it's called the RFC 2547 BIS VPNs, and that is more like a historical name because this is the RFC that it was known from for quite some time now. The RFCs, the Internet Standard Documents, have been developing since, and now they are really actually at RFC 4364 for standardizing these kinds of VPNs. The difference, one significant difference here is that all the VPNs are really, in a sense, in the same address space internally in the provider's network. So it's not that we are dividing the routers and the routing tables into different parts. Instead, they are all in the same space. So which means that the routing tables, we need to have internally inside the routers, we need to have prefixes. We have something, we need to use something internally that says, well, this particular packet, this particular routing table to be used to this VPN. So we need to tag on a VPN identifier internally that sort of associates and says that this is the VPN that this thing belongs to. And it also means that all the PEs, all the provider edge equipments, all the equipment that is interfacing to the customers, they need to be aware of all the VPNs that are around in the system. And somehow figure out when something comes in on this particular interface, I know that it belongs to this and that VPN, and then we tag on this internal tag that we use inside the route to distinguish this VPN. And then we strip that information when we put the packet out on the network again. So that means that the routing table inside a VPN router is not only the operation that this box this router is doing is not only to map an IP address to an outgoing interface. Instead it's mapping a tuple, a VPN identifier, and an IP address is mapped onto an outgoing port. Still, and the lookup operation is, of course, this is usually IP forwarding, which means that the lookup is based on the destination address in the IP packet. And it means that in order to achieve this, our PE routers, they need to communicate using the routing protocols, the standard routing protocols with the customers to learn all the customer addresses, all the IP addresses, prefixes that the customers are using inside their VPNs. And those need to be stored in the routing table inside the router. And this turns out to be a bit of an issue. So this is a real example from a large operator. There was a paper published about this a few years ago. Because what happens in the provider networks is that the VPN part, the VPN services, are taking over compared to the regular internet services, the regular internet connectivity services that the provider is offering. So there are cases where the VPN part of the routing table is an order of magnitude larger than the regular, the parts that are related to the internet, to the basic internet. So 2 million VPN routes versus 300,000 internet routes. This comes from Orange, I believe. And And this creates problem inside the provider network, because what the routers need to do internally is that they need to propagate this information between each other, saying that, okay, here I am, I'm a router, and I'm connected to this particular prefix, and I need to distribute this information to all the other routers so that you have a consistent view of where the different customer VPNs are. So the basis for routing is that all the routers should have a consistent view of what the network looks like. And this is something that slows down communication between the routers. Just transfer these large tables between the different routers back and forth inside the provider's network. And when a change happens, the information about the change has to be propagated to all these different, to all the involved routers, and so on. And it turns out the result of this is that it turns out that the limiting factor for performance or capacity in this network is really the capacity for communication of router control information. So it's not the data traffic in itself that is the problem. It's not the data switching capacity that is the problem. It's the capacity for sending this control traffic, sending these large routing tables back and forth between the routers. That is the main performance issue. So providers find that they need to upgrade their network, not because they're out of packet switching capacity, but because they are out of control plane capacity. And it is a bit annoying, of course, finding that it's not really the data plane that is the limiting factor, but the control plane. And part of this comes from the fact that VPN is something that has been built on top of existing protocol. It's a functionality that has been added to existing protocols, in particular to BGP, rather than engineering protocols from the beginning, saying that this is the best way of supporting VPNs. We found that, well, there are existing protocols that we can modify a little bit to include support for this functionality as well. But those protocols also have a kind of behavior, but is not really dimensioned or intended for this kind of communication. So it turns out that this actually becomes a bottleneck for some providers in the networks. And this is an area where there is really no simple fixes. So in order to get around this, some re-engineering efforts are needed, whatever that might be. Okay. So that was the first way of doing layer 3 VPNs. We're using MPLS together with BGP. And the other way is, well, quite similar to what we already talked about. How can we build virtual networks out of virtual routers and virtual links? We virtualize our routers so that we divide them into multiple smaller virtual routers. And every customer will be communicating directly with one of these virtual routers. It doesn't see that this is a part of a large physical router. Instead, we're communicating directly with the virtual router, and that is what the customer sees. Each virtual router has its own routing table, routing processes, interfaces, and so on. And then we can use MPLS internally in the provider network and use MPLS labels to identify the virtual routers or the virtual network to which this particular packet belongs. So when a packet comes in, an MPLS packet comes in, we look at the MPLS labels and use the MPLS labels to identify the virtual router inside the physical router that this particular packet is going to. And then when we're sending it out again on the network, we are putting another MPLS label on it so that we identify it for the next hop router and so on. So this was a fairly quick walkthrough of layer 1 and layer 2 and layer 3 VPNs. A little bit of a summary of the protocols in VPNs that we use for VPNs. We have IP as a basic information carrier, of course. We use MPLS for the tunneling through the provider network. So the MPLS is not really something that the customer sees, it's something that the provider is using internally in the network. We didn't talk very much about RSVP, but RSVP is a protocol that we're using internally to set, also internally inside the provider network, to set up the MPLS paths between the provider's routers. Then, of course, the provider internally needs to use some sort of an internal routing protocol, intra-domain routing protocol, so to find the best way through the provider's network, and then it's up to the provider if he wants to use OSPF or ISS or RIP or whatever. We use BGP for the distribution of the reachability, for the discovery functionality. And then finally, we need to agree on what is the interface between the customer edge and the provider edge. So there needs, because there should be, if you remember, there should be a routing interface, routing protocol interface between the provider and the customer, and we need to agree on a protocol there. So it's quite a long list of different protocols that we need to use in order to get this virtualized private network service. So far, I've only been talking about provider provision VPNs, where the provider is selling a service which is about interconnecting the corporate's different offices and branches with the virtual networking service. But we don't need to go to the provider in order to do this. If we want, we can do this ourselves. We can set this up in our computers. Create VPN between all our computers in here, for instance, using pretty much the same kind of IDs that we will we set up tunnels across the provider networks. The difference is only that the tunnel endpoints are in our computers. It's not in the routers that are sitting around in the system. The tunnels are ending in our computers. I guess maybe some of you have been running OpenVPN. OpenVPN is an open source VPN solution that you can just download and install and run on your computer. And what it will do is that it will create a virtual interface inside your computer. And that virtual interface then represents the virtual network. When you send something out on that virtual interface, it will be encrypted using TLS. And will be sent over the network to the other side of the VPN. And then you can configure it as point-to-point tunnels, or you can set up an open VPN switch, if you like, which is going to act like a little bit like an Ethernet switch that is going to switch packets between the different tunnels. So if we want, we can do just VPNs, virtual private network, on our own inside our computers. We use this quite a lot as KTH when we need to do networking experiment in student courses, and then we don't want to let the students experiment on the production network, so then we set up open VPN tunnels instead, and the students are using that for their experiments. All right, just for the sake of completeness, I wanted to have a couple of slides about user-based VPNs as well. So, to summarize, VPNs, they happen at different kinds of level, layer 3, layer 2, layer 1 VPNs. But regardless of that, in the provider network, the technology that we're using there, that the providers are using, are still very much the same. We're using overlay tunnels, different kinds, through MPLS. We use BGP RSVP for discovery and for setting up the label switch path for MPLS. And then my final comment about VPNs and is that they are, even though it seems like a fairly simple service, it's very easy to quickly explain what VPNs is about and what the idea is. So it's simple conceptually, and also what you need to do from a configuration and setup point of view is also fairly straightforward and not really so complex. But when you start looking into the details about the different protocols that are involved and how they are related to each other, it actually gets very complex to get into the details of VPN. That is my personal remark. Okay, VPNs are something that has been around for quite some time. There was a good article in IEEE Communications magazine in 2004. We summarized the basics. There happened a few things since then, but this summarizes the basics of VPNs. So that is a good reference if you want to read more about this. Recapitulate a little bit of what we've been talking about. This will be about router virtualization. I will, from the context of building, one of the main building blocks, one of the tools that we need, one of the components that we need in order to build virtual network. We need to be able to virtualize our routers. And I've been through this already. One of the reasons we are doing this is because we're going to do resource sharing. We would like to do outsourcing and offloading of network operations. There is support available in commercially available routers, Juniper, call. There are actually different flavors, but one of them from Juniper is called logical systems. Nowadays, it used to be called logical routers. And Cisco has something which is called the secure domain routers, which is available in the larger systems, in the 12,000 and the CRS series. So they are virtualized, so that the hardware can actually be divided into several virtual routers. I will not be talking so much about the commercial aspects and virtualization of hardware routers. So what I will be talking instead is about open virtual routers. So what I mean with open virtual routers is something which we build on commodity hardware, typical regular server computers, computer hardware. So it's built on commodity hardware and open source software. And what we would like to achieve here is that we would like to be able to support multiple independent virtual router instances at the same time on top of this commodity hardware. In order to do this, we will be using regular virtualization technology. We'll be using software virtualization, operating system, computer virtualization. And this is something that will put restrictions on what we can do, and it will also make it possible for us to use certain resource policies among the virtual routers. So we'll be able to say that, well, this particular router will be able to use this kind of resources, and so that we can partition the resources inside our system in such a way that different virtual routers will get different kinds of resources somehow, depending on what virtualization technology we are using. All right, and the ultimate goal then, of course, is to we'd like to have achieved that each virtual router maintains its own virtual network interfaces, routing protocols, routing tables, management protocols, packet filters, everything that we like to be able to do with the real physical router. So why do we want to do this? Why is this interesting? Well, first of all, I mean, we are researchers, so we like to work with open platforms, and being able to use open source virtual routers is a very useful and powerful tool for experimentation and development for us. But there are other reasons as well. Because what is happening now with cloud computing and computer virtualization is that we are running virtual machines. We are not running real machines, we are not running physical machines, we are running virtual machines. So on the same piece of hardware, we will have many virtual machines running at the same time sharing the hardware. And if we have that, multiple virtual machines, we need to have a way of interconnecting those virtual machines with each other. So this means that there will be a switching functionality inside the computer, inside the server. So for virtual machines, virtual computers, we need to have virtual switches as well. And those virtual switches need to be implemented on top of the commodity hardware, which means that they will be software switches. We could use the Linux bridge. The Linux distribution by default includes a bridge component, so they already have bridging software. And if you connect that to virtual interfaces inside the computer, well, then you have this virtual switching functionality. A software switch is a switching packet between virtual interfaces and thereby between virtual machines inside the computer. There's something which is called an open vSwitch, which is an open source effort to do this kind of a virtual switch. It runs on different kinds of virtualization platforms. And what is happening here is that we are really blurring the distinction now between hardware and software. What is running as a virtual machine and what is running as a physical machine. So we will have a network, in a sense, consisting of virtual machines running on different physical servers. And to interconnect those virtual machines, we are using virtual switches and probably physical switches, and they create a network. So this means we'll have networks which consists of virtual switches and physical switches. And from the outside, we don't really see a difference. From a network management point of view, we don't see a difference, and we don't want to see a difference. We don't really care if this switch is in software running inside the server or if it's a physical piece of hardware running somewhere. We want to be able to manage them, control them, and configure them all in the same way with a common interface. So from a network management point of view, we don't want to care. It used to be in computer server farms that there were two kinds of guys, those that were running the computers and those that were running the network. And when the network started moving into the computers, then we got into problem. Who is in charge of the network, the virtual network inside the computers, and who is in charge of the physical network? Is it the computer guys or the networking guys? All right, so what is it that we can, what are the different tools here? First, there are two main kinds of virtualization technologies. Hypervisor-based, which means that we have a piece of software which is virtualizing the hardware and virtualizing the system and making it available to the virtual machines or the guests. Examples of those are KVM and VMware and Xen and those others that I'm sure that you've heard of. And then there's a slightly simpler form of virtualization, which is called container-based virtualization. And here we don't virtualize the underlying hardware. What we virtualize instead is operating system resources. So virtualizing the file system, the process identifier space, we are virtualizing libraries, and so on. So this is also something called a shared kernel, which means that all the guests, all the virtual machines, will be running on the same operating system kernel. So if you have installed Linux of a particular version, that is what all the guests will be using. You can't have one guest using one version of Linux and another guest using another version, or another guest using Windows or so on. They will be all sharing the same operating system kernel. And there are some other examples of container-based virtualization. This sort of illustrates what it is that we are ultimately after. There are two guests, two clients, two virtual routers. They are with the routing protocols. FIB, which means the forwarding information base, is a routing table that we use for lookups, which is being created and updated through the routing protocols. And then we have virtual interfaces where packets are coming in and out. So those yellow parts, they appear to be routers for all practical purposes. And then we need to have a way of directing packets from physical interfaces to virtual interfaces. That's another kind of functionality that we need to have in the system. So a packet comes in on a physical interface. We need to look at this packet and decide, this packet belongs to virtual router number 1. So I'm going to put it on the incoming interface of virtual router number 1, VIF1 in this case. Another packet comes in, we have to say this belongs to virtual router 2, so we should go to VIF1 inside router 2. So that means, A, that we need to have a way of identifying the virtual router to which a packet belongs when it comes in. We can do that through VLANs or looking at the MAC addresses and so on. So we need to have a way of uniquely identifying the virtual router to which the packet belongs. And we need to have this software switch. We need to have this functionality of transporting the packet internally in the system from physical interface and putting it in the incoming queue of a virtual interface. Those are the two kind of functions that we need to have inside the system in order to support the communication between the virtual routers and for the physical router. So then there are some challenges. One of them is that virtualization, it has a certain overhead. We know that. We know that it's going to cost us. The virtualization itself has a certain cost. There are performance penalties because of the overhead. There will be multiple context switches where we're switching between processes, between virtual machines, and context switches cost us in terms of processing time. There will be some internal packet processing overhead as we are transporting the packet inside between the different interfaces, virtual interfaces, inside the virtual machine. So that's one of the challenges here. Another one is that, can we do this in an existing system? Can we use the available software modules that we have in Linux or some other system? Can we use that in order to create an open virtual router with minimum virtualization penalty? So that is the other challenge. And now I'm going to look at a few specific examples and say that, well, and have a look at how this could be done. And I'm going to start with container-based virtualization. And the reason for that is that the container-based is at least supposed to have the lowest overhead. This is supposed to be the most efficient way of doing virtualization because everything is happening inside the same operating system kernel. We don't have to switch from the host machine to the guest virtual machines. Everything happens inside in the same context, in the same operating system kernel. So the first case is something called OpenVC. This is an open source virtualization package for container-based virtualization. This is also being commercialized by a company called Parallels Incorporated, and they call it Virtuoso Containers. They use virtual devices, two different kinds, VNet and virtual Ethernet devices, VETH. I'm not going to go into the details about that. But for the mapping, in order to transport the packets from physical interface to virtual interface, they are using the Linux software bridge. So you can think of it as a simple bridging function between internal interfaces in the operating system. So packet comes in on a NIC, on a network interface card. It ends up in an input queue. It goes through the bridge, which says that, this particular MAC address belongs to virtual router number 1, and puts it in the incoming virtual Ethernet interface for virtual router number 1, where virtual router number 1 is going to pick it up, do the IP forwarding processing, putting it on an outgoing queue. Virtual outgoing queue, it goes through another software bridge in order to end up on the outgoing interface side. So this is straightforward. We take what we have in terms of virtual interfaces, in terms of functionality for switching packets between virtual interfaces, and put them all together in order to achieve this functionality. And then have some performance numbers for that to show that we are actually paying quite a lot in terms of performance penalty for doing this. The blue line, I don't have my laser pointer now, the blue line shows the throughput in terms of packets per second, 1,000 packets per second, versus the load, so the number of packets per second that we are inputting to the system. And then you can see that it follows a straight line, which means that it can deal with all the traffic that we are putting into the system up to something like 400,000 packets per second. And after that, the performance starts dropping. So then we reach the maximum performance that we can get with the system, and then the performance starts going down. The red line is a system without virtualization, so as a reference with the software bridge, only with the software bridging function, which has almost twice as much in terms of capacity before it starts declining. So we see two things here. One of them is that well, we pay a lot in terms of just throughput. We can't get as far as we can with the Linux bridge when we use with OpenVC virtualization in this way. So that's one thing we learn. The other one, which is perhaps more severe, is that we see the performance starts going down. So there are clearly some when we reach the maximum throughput. So you see that from 4 and 5 and 600, that we get a decline. The performance throughput starts to go down. And that is clearly not a good thing. That is not something that I'd like to see in the system, because what it says is that when you start putting more and more load onto the system, some internal things start happening, which is actually decreasing the performance. So ideally what you would like to see is that you come to the maximum performance and then you get a straight line that just flattens out. And maybe I should go back to this one instead. And the reason for why this is happening is that is very clear in this drawing. Because what happens is that we will start dropping packets in the queues that are in the second or third or maybe even fourth stage of this change. So we have a queue, we have some processing function, we put it in another queue, we take it out from that queue, we process the packet a little bit more, put it in another queue. And queues are finite resources. There's a finite number of places in a queue, right? So that means that when a queue is full, we're going to drop the packet, and that is what's happening. That is where we're losing the packets. We are dropping them in queues. And when we have something that looks like this, so we have multiple queues in chain, and then we have some processing function happening between them, it means that we will do some processing of a packet, put it in a queue, and try to put it in a queue, but it might turn out that that queue is full, and then we're going to drop the packet. And when that happens, we do partial processing of the packet and then drop it. It means that all the processing that we've done for that particular packet is wasted. It's useless cycles. We spent those processing cycles in vain. So that is what is happening when the blue curve starts going down. We are processing the packets, and then we throw them away. Processing the packets a little bit, throw them away, which means that you're spending CPU cycles processing packets which are only dropped. If we should drop a packet, we should do it as quickly as possible, as early as possible in the chain. And if we don't drop it there, then we should really try to take it all the way through the chain. That is what we ideally would like to have. We do not want to have drop points in the middle of the packet processing chain, because then we get this kind of behavior. So that is, I'm not sure if you follow that reasoning now, but that is what is happening, and that is what is causing the curve to go down. So we can live with degraded total throughput, but we don't want to have a system that degenerates at high load. We don't want to see this kind of congested behavior. So what can we do about this? Well, first, there are two things that we'd like to change. The first is that, well, this bridging software that we're using in order to connect virtual interfaces to physical interfaces is a general purpose software switch. It has all the functionality of a real switch. It does all the learning and flooding and MAC address lookups and so on. And those operations are really not necessary. We are not using them in order just to get this functionality. We're connecting a physical interface to a virtual interface. So we can. So the first step would be to say that, well, let's try to get rid of that functionality. Let's try to do something which just does a straight mapping, take the incoming packet, analyze it, look at the MAC address, and say that, okay, so this particular MAC address belongs to this virtual interface, and then send it there directly, without doing the Ethernet bridging processing, without doing the learning and flooding and all this overhead. So that could be the first step. There is one such device in another way of doing container-based or shared kernel virtualization in Linux, and that is called Linux namespaces. Is also known as LXC, which stands for Linux containers. LXC is the program that you use in order to configure this kind of containers. So that is what the name but you may know that if you've been working with it. LXC is the name of the Linux command. And by doing that, we get rid of some of these queues that are sitting there in a chain. So we get rid of some of these potential drop points, because we're creating straight path directly from the physical interface directly into the virtual interface, the MAC VLAN, and then is where the guest will start picking the packet up and do the processing. This is going to make it a little bit better for us. You see that the performance now is going up, and we also, this is the green curve in the middle between the Linux bridge and OpenVC, and the OpenVC case that we saw before. And the reason for why this is improving is now we're getting the dynamic behavior that we really would like to see. We're dropping the packets as early as possible, as close to the physical interface as possible, and if they get past that point, then we're going to take them through the whole chain. And there's one more thing, a further thing that we can do in order to improve the interface work, and this is something that has been done. This is work also that comes from partly at least from a person working at KTH. Robert Olsen has been involved in something that's called NAPI, which is a new API for packet processing. And the idea here is that we are still dealing with physical devices, and interrupt processing is a very costly operation. So the default behavior where you get one interrupt per packet is something that is going to cost a lot in terms of performance, which is okay for lower packet loads. If you don't get a lot of traffic, then it's okay to take an interrupt for every packet and bring it into the software and start processing it. But at high load, we don't have the time to take one interrupt per packet. So what we would like to do instead is to try to do it in a more batch-oriented style. So instead, what we'd like to do instead is to do software polling, check the interfaces, see are there more packets coming in at the same time. In that case, we process them during the same interrupt processing cycle. So and the good point with doing that is that by doing that we get rid of even more internal interfaces, and internal queues. Because once we've figured out that there is a packet available for input processing on this particular hardware interface, then we pick it up and we bring it through the whole chain, the whole packet processing, the whole packet data path, and put it on the outgoing interface. So this is the ideal picture. This is what we really would like to have, and this is what we achieve with NAPI enabled at high load. And now we're getting much closer. Well, not on this one, but on the next one. This is in this scenario we are using, now let's see, multiple interfaces. We're using more virtual interfaces internally. If you're just using two virtual interfaces internally, then we don't really see a big difference between MAC VLAN and MAC VLAN with NAPI running. But if we start adding a number of interfaces, then we see that just MAC VLAN, we are getting back to this bad behavior, this degenerated behavior at overload, where throughput is going down as we increase in the load. While for NAPI MAC VLAN, the case where we have this more clever interrupt processing and this direct mapping from incoming interface to virtual interfaces, we get the behavior that we ideally would like to see. We get a straight line at the overhold condition. We're still paying a performance penalty for doing virtualization. We still can't get the same performance as our base case, as our reference case, which here is regular IP for forwarding. So we're still paying a little bit in terms of performance for the virtualization due to the overhead that we are seeing in the virtualization. All right. So this is as far as we come with we have still been using the regular Linux software, regular Linux, regular Linux implementation of IP, and the regular software for standard interface cards. But as things have been evolving, the vendors of hardware have realized that this is an important kind of functionality, and particularly for servers. Where servers running in server farms, we're supporting many virtual machines. We need to be able to control the traffic in a better way. So now there are hardware support coming up on network interface cards for virtualization and for dealing with multiple virtual machines at the same time. Now, this hardware support isn't really designed to begin for virtual routers. It's not for networking. It's really for servers, which means that we need to be a little bit careful if we want to use this, because some of the functionality that is there is really completely counterproductive if you want to do virtual routing. It actually turns out that it decreases the performance if you turn it on. So we need to be a little bit careful. But let's just have a quick look at the kinds of hardware support that is available for creating virtual routers on commodity hardware. Well, first of all, we have multi-core CPUs. All modern machines have more than one CPU core in them nowadays. So then ideally what we would like to do, of course, is to say that, well, this core is going to run virtual router this and that, so that we assign or pin different virtual routers to two different CPU cores. And the reason we want to do this is, of course, is to work around caching problems. We would like to make sure that all the packets that belong to the same flow are going to the same place, going to the same virtual routers, so that we maximize the probability of getting cache hits, because that is going to be important for performance. Modern network interface cards have many queues on them. It used to be that a network interface card had one interrupt queue, one input queue, where the packets are being stored. But now, modern network interface cards, they have multiple queues. So they maintain virtual queues and hardware, which means that we can assign virtual queues to virtual routers, which is one good starting point. And then there is, and on top of that, we're going to use something which is called SRIOV, Single Root I/O Virtualization, which means that there is, see if I can get this right now, which means that there is support in the NIC hardware for having virtual interfaces inside the operating system. So there are hardware support for having multiple interfaces, multiple Ethernet interfaces. Each of these virtual interfaces is going to look like an Ethernet interface. It's going to have its own MAC address, and so on. And it's going to have its own interrupt line as well. So we're going to have different interrupts and different interrupt line associated to different input queues. And then finally, we know that one of the main issues with running virtual routers as guests is that we need to, when a packet is coming in, it's going to be stored in memory somewhere. And that memory is going to be in the memory address space of the host operating system. But that's not where we want it to be. We want it to go into a virtual router. So we want it to be in the address space of the virtual machines where the virtual router is running. And we can do this by copying data, shuffling data around, and moving it between memory areas, memory buffers inside the operating system. But that is going to be costly. This is going to cost us in terms of performance. So what we really would like to achieve is we would like to have the memory, the hardware and the memory management hardware on the network interface card to throw the packet straight into the buffer memory of the guest. So we need some hardware support for translating between guest and host memory address spaces, and we need to be able to associate DMA transfers, memory transfers, and interrupts directly to our guests. And luckily, all of this functionality is available on advanced and modern network interface cards. So what we finally would like to have is something that looks like this. So the packet comes in from the left. The network interface card, the NIC, the hardware, is going to look at the MAC addresses of the packets that are coming in. And depending on which MAC address it has, it's going to put it in a different incoming queue. From that queue, we will generate an interrupt which goes directly to one of the CPU cores, the cores that we have pinned this particular queue to, saying that this is an interrupt that belongs to your particular queue. The packet goes straight into the guest memory address space of that particular virtual router, and it gets interrupted and can start pick it up from its incoming queue and do the packet processing. So this is what we can build. So and what it shows here is that we have 4 different cores, 4 different CPU cores. So each has its own virtual interface queue. It has its own interrupt lines, and the hardware is going to send packets straight into these cores and into the memory space of the guests that are running there. And let's see. This shows the performance. And what we get here is that the blue column shows regular IP forwarding performance, regular IP throughput. So without virtualization, one single router, non-virtualized routers. We see that the performance is going up as we increase the number of cores. If you have good eyes, you see that it's not increasing linearly, it's flattening out a little bit, but it's going up with the number of it is increasing with the number of cores. The red bar in the middle is the previous case that we saw, where we're not using any particular hardware support. We are using software the best we can with NAPI and MacVLAN and LXC and namespaces and all that stuff, which was the best that we could do. We see that the performance is also going up with the number of cores, but we're still below the reference. And then finally, if we enable all the hardware stuff and all the fancy things that we saw on the previous slide, we get the green bar. And then we see that it's interesting that we are better than the virtual router without hardware support, but we are worse than the plain IP forwarder without virtualization for one CPU core. But as we start increasing the number of CPU cores, we can actually do better finally than the blue case, than the plain IP forwarder without virtualization. Okay, there's a lot about performance here. I'm going to show a little bit more of this, because so far I'm only talking about container-based virtualization, LXC and LXC namespaces and OpenVC. And the other, but the question is, how does this then compare to full virtualization, where we're using a hypervisor instead, which is virtualizing the hardware, which makes it possible for us to run any kind of a guest operating system on top of the hardware. In this case, we are running Linux again, a different version of Linux, but we're running it as a guest inside KVM. The scenario that we get then is the left one. So it means that we are moving all the packet processing functionality from the kernel, the host kernel, the namespaces kernel, and we're moving it into the client instead, so the guest virtual machine. So that is where all the packet processing is going on. And that means that then we really have the flexibility. In the red part, in the guest machine, we can implement any kind of packet processing we like, any kind of protocol we like. It doesn't have to be supported in the host. It only needs to be supported so much so that the host knows that this kind of packet should be delivered to this particular guest. But then what the guest is going to do, it is completely up to the guest, and it could be a protocol that is not even supported by the host machine. So that is something that we will be able to achieve if we do it in the left way, using KVM in this case as a full virtualization technology, hypervisor-based virtualization. And then we're comparing it with LXC's namespaces. And what this shows is that, well, it shows a couple of things. All these lines at the bottom here are performance numbers for KVM, which are performing, as you see, very poorly. Then you see there's a very high performance penalty for doing full virtualization, for doing para-virtualization, due to the context switches going between the host operating system and into the kernel operating system running a Linux user space. And the context switching involved going between those is costly, very costly from a performance point of view. But if we enable the hardware support, which are the ones towards the top, then we can see that there is very little difference. There's a very little penalty for using KVM compared to LXC. KVM is almost as fast as KVM. The red is the red and the black one. The red with the crosses and the red with only a horizontal dash. It's marking that's the KVM, and LXC with hardware support, and then they're very close. So the conclusion to draw from this is that full virtualization, hypervisor-based virtualization is very sensitive in terms of performance for what kind of support we're using in the system for virtualization. But with hardware support, we can get almost close to very close to the container-based case. All right. So, what are the conclusions from this? Well, the design of the internal data path is extremely important if you want to do virtual routers. In particular, you want to do them based on open source and open platforms. This is not what the system was designed from the beginning. And we have to be very careful with how we're using the system, how we configure the system, if we worry about performance, which we probably do. There's a high penalty for all cases, both for LXC and for full virtualization, if you're using just the regular software, the regular packages that come with the Linux distributions and that are there, and the plain network cards. But if you're a little bit careful with how you configure your systems and invest in modern network interface cards with hardware support for virtualization, mainly hardware virtualization support for server virtualization, but if you're careful with how we use them for our virtual routers, we will be able to get a good performance with that too. There'll still be a little bit of a performance penalty compared to the non-virtualized router, but we're getting very close if you're careful with how you're using the hardware. And then I write virtual routing for virtual computers. The bottom line to emphasize that why is this important? This is not only us as researchers that are interested in open source platforms because we can do experimentation with them, but we're also moving into a world where the distinction between hardware and software is getting blurred. We're mixing software switches with hardware switches mixing hardware switches with software switches. Software switches running on commodity hardware, and that means that the performance of those are going to be very important for the performance